Okay, so we're on chapter 4, which is applications of derivatives. So this is one of the most interesting applications of derivatives, at least what I think so. And it's called using the derivative to make a linear approximation of a function. So I'll explain what we mean by that. So let me go into writing mode. Okay, wrong writing mode. There we go. So a good example, why do we need a linear approximation? So I'm going to put in, there we go, axes, x, y, and then let's use the function of sine. Okay, so let's say that this is f of x equals sine x. Okay, so we know that f of 0 is 0. So that's this point right here. And I'm going to draw in a little line. Oops. Okay, let me draw in a line, please, computer. There we go. Okay, so let's say that's the tangent point at 0. The tangent line at x equals 0. Close enough. Okay, so we know what the sine of 0 is. What is the next value of sine that you know? So if you were to go in order, f of 0 equals 0, what's the next value of sine that you know how to compute? No, you don't know how to compute f of 1. They're usually in terms of pi. Like for instance, right here is pi over 2, which is going to be 1. Maybe that's what you're thinking of. F of pi over 2 is 1. But what's another one that you know? So f of pi over 2 is 1. That's this point right here. But what's another point that you know on the sine graph that's close to 0? Like off the top of your head. Pi is all the way over here. That's not closer to 0 than pi over 2. Pi over 4 is a good one, yes. And actually I would say the closest one is pi over 6, which is 30 degrees. But f of pi over 4 is root 2 over 2. What's the sine of 30 degrees? Like 1/2 or something like that, right? So let's just draw a little thing. Here's pi over 6. Okay, so in other words, you know what the sine of 30 degrees is. It's 1/2. You know what the sine of 0 degrees is. It's 0. What if I asked you for the sine of 7 degrees? Would you know how to calculate that? Without a calculator, by hand. Do you think you could do that? No, good. Yes, you'd be like, I have no idea what to do. So what we're going to do is this. We're going to use the tangent line to approximate a value that we want. So let me draw the picture. Let's say that here's your f of x. And you know how to plug in the value a. So when you plug in a, you get f of a. And you're like, yay, I know what f of a is. And let me draw my little line. There's the tangent line at f of a. Now, you want to know the value of the function right over here, which is a plus delta x. You would like to know the y value of f of a plus delta x. So this a, for instance, is sort of like plugging in 0, and this a plus delta x is sort of like the 7 degrees. You know what the sine of 0 is, but you don't know what the sine of 7 degrees is. You know how to plug in one of the values, but you don't know how to plug in the other value. Okay, that's what we're going to use, or that's what we're going to use the tangent line for. Because if you look at the tangent line, do you see this little red dot on the tangent line? Do you see how it's pretty close to this blue dot that we want right here? So this blue dot is the value that we want. We want to know what f of a plus delta x is. And what we're going to do is we're going to find this point on the tangent line. And we're going to use that point on the tangent line to approximate the value that we want. Okay, so remember, the tangent line is determined by y minus y naught equals m times x minus x naught. Okay, so the y value that we're going to be using is f of a. The y naught is f of a. We'll get to m in a second. The x naught is a. Okay, now the m value is the slope of the tangent line at a. Right? Because that green tangent line, that's the tangent line at a. So together, this gives you y minus f of a equals f prime of a times x minus a. Which gives you this, if you move the f of a over, you get y equals f prime of a times x minus a plus f of a. This is your tangent line approximation. What you do is you're going to take the value that you want to plug in, the a plus delta x, and plug it into this formula. So if you plug it in, you're going to get that f of a plus delta x is approximately equal to f prime of a times, now the x value that you're plugging in there is a plus delta x minus a plus f of a. So what you notice is that the a and the plus a, the a and the minus a cancel, leaving you with f prime of a times delta x plus f of a. So if you want to approximate a plus delta x, if you want to approximate f of a plus delta x, that is going to be close to f prime of a times delta x plus f of a. This is called the linear approximation formula. So this is your linear approximation formula for f of a plus plus, where's the delta for the delta? Come on, where'd you go, delta? Ah, there we go. F of a plus, okay, just had it. There we go. Sorry. F of a plus delta x. It took me like way too long to find that. So the linear approximation for f of a plus delta x. That's what this is. So if you want to approximate that, that's what we're going to do. So this allows you to do things like, hey, I want to know what sine of 7 degrees approximately is. Okay? You don't know how to calculate that. So what you're going to do is use the tangent line at sine of 0 to make your estimate. Okay, so let me give you an example of like how this actually works in practice. In practice. Okay, so example. We are going to estimate the value of the square root of 9.1. my god, I can't type today. So our function here, our f of x is the square root function. And let's put in our drawing of the square root. Square root looks something like this. Okay, now we want to know this value right here, the 9.1. Now, what is a value of the square root very close to 9.1 that we can actually calculate? You don't know how to actually calculate the square root of 9.1, but what is a value close to 9.1 that you could calculate? Square root of 9, exactly. So that's going to be your a. Your a is 9, which means that a plus delta x is 9.1. Now, if a equals 9 and a plus delta x equals 9.1, that means that your delta x is 0.1. And that should make sense because your 9 and your 9.1 are 0.1 apart. That's what your delta x is. Okay. So what are we going to do? Well, we are going to find the tangent line at 9. So here's like your tangent line at 9. And then what we're going to do is find the point on that tangent line. And actually, you could see in the graph, the point, the tangent line at 9.1 is very close to the square root at 9.1. So those y values are going to agree. So we are going to, so let's use the formula. The formula says the y value, which is the f of a plus delta x that we want to approximate, is very close to f prime of a times delta x plus f of a. We want to approximate 9 plus 0.1. So we need to plug 9 into our derivative, multiply by 0.1, and then add the value of the function at 9. Okay, so we need to know what the derivative is. Well, if our f of x equals x to the 1/2, then our derivative of x is 1/2 x to the minus half, which is 1 over 2 root x. So if you plug 9 into that, you get 1 over 2 root 9, which is 1/6. So the f prime of 9 is 1/6. So you get 1/6 times 0.1 plus f of 9. F of 9 is 3, right? Square root of 9 is 3. Point 1/6. So 1/6. That's so let's do this. 1/6 times 0.1 is 1/10. So I guess, okay, we'll just use a calculator to do that. What is 1/6 times 0.1? So 1 second while I calculate that. Come on, computer. Calculator on. Failing me. So what is 1/6 times 0.1? Yeah, 0.016 basically. So let's write that as, so we get 0.016 repeated, so I'm just going to write 0.016 plus 3, which is 3.016. So this is telling me that the square root of 9.1 is approximately equal to 3.016. And if you go to something like a calculator and calculate the square root of 9.1, let's see what that is. Oh my god, I'm like having such problems typing today. You get that it's 3.0662. So do you see how those are like pretty close to each other? Like they agree up until what, the third decimal place, right? Okay, so historically, this is what they use to calculate values that they especially before like the invention of calculators. Like I'm not going to explain to you how the calculator figures out the square root of 9.1. I mean, we have ways to do it now. But the cool thing is that historically, when people didn't have calculators and they needed to do something by hand, this is what they would get. And so like what they would usually do is write it as a fraction, because the 1/6 times 1/10 plus 3. So they'd say, oh, the square root of 9.1 is approximately 3 and 1/600th. Right? That's what that number is.